All right, so last time we did the density operator, for us always a matrix. And here's the summary for you, very brief summary. Rho is the sum over I of real numbers pi that add up to 1, and then quantum states psi I. If it's the case that all the probabilities are 0 except for one of them, in other words, rho is the outer product of some wave function psi, we say that rho is a pure state. Otherwise, it is a mixed state. And we also defined the purity last time. The purity is this quantity trace of rho squared. And as a theorem, we stated the theorem, we didn't prove it. I will ask you to prove it in the homework, I believe. The trace of rho squared, the purity being 1, is equivalent to the state being pure. And otherwise, if the trace of rho squared is less than 1, then it is a mixed state. We also covered the partial trace. That tells us how to go from a composite density matrix, rho AB, to one of the component density matrices, for example, rho A. And to do that, we have this operation, the partial trace, where I trace over one of the subsystems, for example, here B. And we define that as, given a basis indexed I for the subsystem B, identity tensor I, basis on B, rho A, B, identity tensor I on B. And we computed some examples the last time. And I just wanted to mention, because I've heard it said from learned quantum information scientists that there's no classical analog to the partial trace. But really, that's not entirely true. There is a very clear classical analog to this, which will perhaps help with your intuition. The classical analog comes from just probability theory. If I have a joint probability distribution, I can calculate the marginal distribution. So, for example, if I had a joint probability distribution, P of x, y, two random variables, x and y, I can consider calculating the marginal distribution. And that would be, for example, P of x. And how do I do this? It's the exact same intuition as what we're doing in the partial trace. I would just sum over the random variable y, so P of x, y. Sum over y, P of x, y will give me the marginal distribution over x. That's the classical analog of what we're doing with the density matrix and the partial trace. Here we're, in a very similar way, summing over it, but we use a basis for these density operators. Similar thing, if you have if it's a continuous distribution, this would just be an integral P of x, y, dy. So this is your intuition for what's going on with the partial trace. This is how to calculate it. The partial trace itself is not a fundamental postulate, but it is actually the unique operation which will yield the correct measurement statistics for the marginal reduced states. So I would encourage you, I'm not going to cover it here, but I would encourage you to check out box 2.6 on page 107 of the textbook to show how the partial trace is the unique operation which gives the correct measurement statistics. So it's not a fundamental postulate itself. It can be derived from the fundamental postulates. So that's why we don't have it as a fundamental postulate. I'm not going to go over this. You can just sort of take it as a postulate for our purposes in the course. But if you're interested in seeing why this is true, check out box 2.6.